So western boundary intensification, or the creation of these strong western boundaries, is one of the most interesting and important physical concepts in large-scale ocean circulation. So here we had this equation for continuity for this fluid, stratified fluid in isopycnal system we are looking at, and we wrote the vorticity conservation using that now as d dt of zeta plus f equal to minus zeta plus f over h times q over rho minus dh dt. So we are writing du dx plus dv dy in terms of layer thickness variability and mass flux, or source sink of mass. That's all we're doing in the previous equation. So we are taking this equation, replacing this from the continuity equation, plus day dx minus dax dy. So all we did was take this from this equation, and here this term, instead of zeta plus f, which we called absolute verticity, we now have it divided by the layer thickness h. This is what is called potential verticity. Why is this potential verticity? As we said, it's because it's a verticity that is in the fluid, which can be released or can be held as potential. And the best way to think about it is ice skating. So this ice skater creates verticity by spinning on her legs, spinning on her one leg and using the other leg to create rotation, and she is on a basically very low friction, frictionless surface, so she can change h. Let's say that's her body length or the width of her arms out, legs out, and so on. So by changing h, she can change her rotation rate zeta plus f. So she has potential verticity, which she can use to spin at different rates by just changing that f. So in the real world, that's what happens. As h varies over space and time, the potential verticity changes. So zeta plus f over h changes. So even if zeta and f don't change and you are remaining with the same relative verticity and the same latitude, if h changes, you can change the absolute verticity. So zeta plus f over h can change. Okay, that's why it's called potential verticity. So writing the equation 1 over h d dt of zeta plus f, total derivative minus zeta plus f over h squared dh dt, equal to minus zeta plus f over h q over rho h plus 1 over h del ax del a del x del ay del x minus del ax del y. So we can write this as assuming again there is no q in a minute, so d dt of zeta plus f over h equal to minus zeta plus f over h. So we have taken h and multiplied the times q over rho h. So we combined these into this, equal to minus zeta plus f over h q over rho h plus 1 over h dy dx minus dx dy. Just stare at the equations, make sure you follow through. I'm going a little fast, but the physical concepts behind these are really, really amazing and worth paying attention to. So the quantity zeta plus f over h is the potential verticity in the shallow water layer. Potential verticity is a conservative quantity in a barotropic and frictionless ocean circulation if no mass is supplied or removed. So if q is 0, and then the pressure terms of producing verticity drop out, so you end up with only the convergence term, and d dt of zeta plus f over h becomes 0, so that quantity then becomes conserved. So again, remembering our shallow water system, regarding this equation 658, wind-driven flow described in the Stommel model can now be understood in a coherent framework. In the Stommel model, a closed flat basin with no mass source or sink, and we had flattened the bottom out with only, so we had flattened the bottom out and we had considered no mass source or sink. with only one shallow layer was considered. We integrate 658 here now over the layer thickness h, which is basically what we had here. So we are considering shallow water layer but as a isopycnal layer for simplicity, assuming again that eta is much less than the water column depth, average depth, which is very sensible assumption, so that h equal to h plus eta just becomes equal to approximately equal to h, and then can be kept constant in the long-term average. Substituting ax and ay for the right hand side of equation 636, which we just looked at, we assume that tau yz equal to 0 according to the Stommel model. So meridional winds were set to 0 and the zonal winds had the simple form T times the cosine distribution. So trade winds in the lower latitudes, easterlies, and the northern domain. So this results in the approximation rho h d zeta dt plus rho h df dt approximately equal to minus tau xz over del y minus r del my del x. Remember, this is the inverse of the decay time scale, the bottom friction term for the zonal and meridional directions, where mx and my were our transports in thickness h, right? So we can look at the order of magnitude of each of these terms for the surface flow with wind forcing, vorticity generation by the winds, and vorticity generation in the boundary layer, to make sure that the vorticity generated by the winds and the mass transport created by the winds because of Coriolis variation with latitude are compensated by the western boundary current to conserve mass and vorticity, and that this can only happen in the western boundary. Okay, so signs of the individual terms in 659 for the Stommel model in the northern hemisphere. The relation shaded in gray is required in order to close the balance terms. Okay, so the large gradients imply a strong confined flow, i.e. a boundary current. So in the interior in the boundary in the interior you have flow going from north to south, so winds are forcing a southward flow. So the rho h d zeta dt term is nearly zero, conserved almost, plus rho h df dt is less than 0 because you are going from north to south, and df dy is negative. Should be approximately equal to winds forcing, which is negative because you remember the relation we had written before for Stommel model winds, and the dmy dx term is nearly 0 and dmx dy term is nearly 0. So the bottom boundaries are nearly 0 in the interior because you are just moving fluid over water column below, and wind-driven circulation you can think of as riding on top of the deeper ocean with hardly any bottom friction. Whereas in the flow that's going from south to north, you again have vorticity that is almost equal to 0, but this time df dt term is greater than 0 because Coriolis is increasing. Wind stress gradient is again less than 0 as before, but now the because you are at the boundary, you have the dmy dx term being much greater than 0. So the vorticity generated here in the north to south interior flow is required to be balanced. So these two are almost going to cancel, greater than 0, less than 0. So you need the western boundary friction term to balance the interior mass balance and vorticity balance. Okay, I hope it's clear. There are many other ways to explain this, but this is the way it's done in the book, so make sure you follow through. And the meridional term is 0 here. So you can think of the friction of the boundary and friction along the flow. So which one is 0? Of course the dmy dx. So the meridional transport is strong and its zonal gradient is very large because it is narrowly confined to a thin layer in the boundary. It's a frictional flow, so its zonal gradient is very large, whereas the meridional gradient of the transport is almost equal to 0. Okay, so Stommel and Arens applied the same model to the deep western boundary flow as well, and the remarkable thing about it was that they did it before there was any data for the subsurface flow, and it wasn't known at all whether there was also a western boundary intensification of the deep water flow. And bravely enough, they used the same model and signs of the terms in the equation for the Stommel-Arens model on the northern hemisphere, doing a similar equation, but this time you don't have a wind stress forcing as we did before. What you have instead is introduction of deep water that is going to drive the forcing of the western boundary intensification. So you have minus zeta plus f q term, where q is the deep water formation at high latitude, and then they wanted to see what happens to the deep flow when deep water forms. So they used the same arguments to show that df dt term is again less than 0 and greater than 0 for the interior flow and the boundary flow. In this case, the boundary flow is from the north to the south because they were assuming that the western boundary current is related to the deep water formation, and the interior flow was from south to north, as opposed to the wind-driven circulation where the interior flow was north to south and boundary flow was south to north. Okay, so this is greater than 0 in the boundary flow because you are putting mass in, and in the interior flow also it's going northward. So again you can look at the sign of f and zeta, and that also turns out to be 0. And in this case again they found that the western boundary intensification will be needed to balance this situation where you have south to north acquiring verticity by flowing from low f to high f, and you need the western boundary intensification to balance it by producing negative f. So verticity conservation again would work. So here is how you can see it schematically. You have trade winds, westerlies, and then polar easterlies at the polar latitudes. Somewhere deep water is forming and introducing a mass source and forcing a boundary flow. So here is an isopycnal. So here we had wind-driven gyres. In the subtropics we had trade winds and westerlies forcing a clockwise gyre, whereas in the subpolar region you had easterlies and westerlies forcing a counterclockwise gyre, both having western boundary intensification, this one going south, this one going north. And Stommel and Arens assumed in a simple way that in the interior there was broad upwelling to compensate for the sinking of the deep water, and the boundary flow was going south but feeding this interior geostrophically balanced flow and getting weaker. Well, that was a simple assumption, and their figure looked like this. So they had northward flow to compensate near surface flow to compensate for the deep water formation, and southward boundary current. Sorry, here in the I'm in the wrong place. In the Pacific there is no deep water formation, so you have southward western boundary current and northward western boundary current with compensating circulation, and similarly here with some kind of a matching happening with the Southern Ocean channel. But in the Atlantic there is deep water formation which is driving southward deep current, and it is being compensated by broad upwelling and return flow in the interior, with other flows happening in the Indian and Pacific Oceans to conclude the large-scale circulation driven by these deep water formations in the Southern Ocean and the North Atlantic. considering this happened in the 50s, this is a remarkable insight. So without any data, theoretically they argued there must be a deep ocean current, western boundary current, and later on data was gathered. Typically, if you go deep at a couple of kilometers in the interior ocean, the currents are so slow that they cannot be directly measured at all. You have to use tracers to estimate the speeds, whereas in the western boundary at 2500 meters they found currents going at 20 centimeter per second, which is remarkably fast current. So the theoretical prediction that there should be a western boundary current was confirmed. We have generally shown Samoa-Highland circulation as this broad sinking southward flow mixing with the deep water formation in the Southern Ocean, inundating the Pacific, converting to surface water, coming back, mixing with the Indian Ocean surface water and going back. It turns out that things are not that simple. There are lots of eddies that are doing a lot of the work, as we said before in the case of atmospheric circulation, which we will come back to again in the next chapter. So Susan Lozier has this nice review paper deconstructing the conveyor belt, where she uses a model, releases lots of very high resolution eddy resolving ocean general circulation model, release a lot of drifters to account for, to see how the western boundary current works, and you can see that there is lots of eddies, recirculations. There is an overall southward flow as required, but it is not as simple as what we think of when we think about the global conveyor belt. This is just the probability of 2D probability map of float locations from the entire set of E-floats over 50 years. So they did this run for 50 model simulation years and showed that the probability that those will remain in the western boundary is high. Obviously, that means western boundary intensification is real, except that it doesn't flow as simply as we would imagine here. Okay, so that's something to remember. So it's a very nice story and a very important story, the most important concept in large-scale ocean circulation in terms of western boundary intensification in the surface layers, Kuroshio, Gulf Stream, East African current in the Indian Ocean, East Australian current in the Pacific, South Pacific, and Brazil Malvinas current in the South Atlantic, and so on. So Vorticity conservation is a big part of that story, because as you move north and south, you are changing F very rapidly, and to compensate for the interior wind-driven vorticity generation or the deep water formation-driven western boundary intensified vorticity generation, you need vorticity generation elsewhere, and the processes are slightly different for the wind-driven circulation versus western boundary deep water formation-driven circulation. Okay.